And we are live.
Okay.
Hey, hello everyone. Glad you could all join us. Welcome to our first guest speaker talk for this year. And we are very happy to have you here. We are an astronomy club here in San Jose, San Jose Astronomical Society. And we have been around for many years, but then this is like I have to say we are in kind of phase of reinventing ourselves right now, where with COVID we are trying to figure out how to keep the club active, how to reach out to people. And this is one of those programs which we have managed to successfully transform. um, and we have a lot more programs, like guest speaker program is one of the things we do, which on every full moon weekend. That's typically because we can't go out and do
Sure.
much
Good
observing on
choice.
that weekend. Yeah.
Yeah.
And then on other nights we actually have in-town star parties on the first quarter and third quarter of the moon, which are currently
Nice.
on hold because
Yeah.
unfortunately we cannot share telescopes.
Sure.
And then for our members, we also have private observing events, which we tried to do a little bit with social distancing when things were not so bad here in Bay Area, but now we
Yeah.
are have stopped that as well.
Yeah.
um, so things are like we are trying to do all of the things that we were doing in a limited capacity.
Mhm.
um, but if you have any suggestions for us or
Mhm.
any other ideas that we should be implementing, please reach out to us on sja.net. My name is Sukhada. I run the guest speaker program. I'm also on the board of directors for San Jose Astronomical
Mhm.
Association. So all our email addresses you can find on sja.net. I will also put this information in the chat so you can find us there as well. And currently, all our events are also posted on Meetup. I hope that's how most of you found out about us. Um, so all the events that we are going to do as and when COVID allows us to will be posted on our Meetup. So with that said, I would like to introduce our speaker for the night. Her name is Adrienne Cool, and she comes to us from San Francisco State University. But I was reading about her, and what's interesting to me is she had like a different background. Like she started with electrical engineering, which is what I started with, so that really caught my attention.
Mhm.
But once she found astronomy, she hasn't really looked back, and I don't blame you. I mean, it's really it's something definitely to do research and have a
Yeah.
career in this field.
Yeah.
And she did her PhD from Harvard, and now she has, I think, it was a postdoc at UC Berkeley that brought her to
Correct.
California, and you have decided to stay. Good for us.
Nice for me.
Um, so, I mean, this is one of the best places on the earth, I have to say.
Yeah.
And so today's talk is like, speaking of Earth, it's really interesting because she's combining these two different things
Mhm.
in this talk, where she's going to talk about globular clusters and binary stars in globular clusters, and then the climate crisis and how astronomers can have effect on fighting the climate change. So with that, I would request you to start the talk, and we are all eager to hear from you.
Wonderful. Sukada, thank you so much for the introduction and for the invitation to come talk to San Jose amateur astronomers. It's really a pleasure for me, and I know the format is crazy for everybody, but we'll try to take advantage of some aspects of it to the extent that we can. At the very end, you're going to see I'm going to share a Google Doc with you to share ideas. If anyone's sitting in front of a computer like I am, you can share your thoughts on that Google Doc. And of course, I would love to hear. I gather I'm not going to hear your voices, but I would love to hear your questions throughout the talk, and at the end, I'll be delighted to answer questions. So yeah, I will say this is the first time I've given a talk quite like this, combining these things in quite this way. But I'm looking forward to it, and we'll see how it goes. So as Sukada said, my research is about globular star clusters. And I'm going to spend the first half or so of my talk talking about them and what's wonderful about them and what's interesting about them, and a bit about what my students and I have been researching about them. for the past almost 25 years that I've been at San Francisco State now. And then I'm going to switch gears and talk about an organization that I co-founded with several students at San Francisco State and a colleague at Yale, Deborah Fisher, who was formerly a faculty member at San Francisco State, called Astronomers for Planet Earth. And I'll say more about what that's all about later. So let me, and I had intended to do something else, but let me just say, globular clusters, why do I study globular clusters? Well, I actually said it even to the person I wanted to do research with, but I remember being hesitant to even say so because they're beautiful. Is it okay to study something just because it's beautiful? Well, many of us do these things, and yes, I'm interested in them because they're just spectacularly beautiful to look at, and I imagine many of you as amateur astronomers and astronomy enthusiasts have looked at globular clusters through telescopes, and depending on what telescope you've used, either it looked like a little fuzzy cotton ball, or maybe with a bigger telescope, you could see the individual bright giants in it, and that sort of sparkling look that they have. That's very beautiful. And well, this is an image that my colleagues and I took some years ago with Hubble of the largest globular cluster in the galaxy, Omega Centauri. It's really hard to see. You really can't see it from San Francisco, but even, southern part of the US, I've seen it from Tucson, and of course it's being in Centaurus, the constellation Centaurus. It's nice and high in the sky if you're in the southern hemisphere, and it's a naked eye object, which is why it has the name Omega Centauri. It's part of that alpha, beta, gamma system. It's at the end of the line, but it is a naked eye object, and so it got into the Bayer designation system. This is Omega Centauri. I'm going to talk a little bit about it later. But let me just start by talking about saying a little bit about what I'm going to talk about. I'll say some background about globular clusters. What are they good for besides just being beautiful to look at? They've taught us a tremendous amount in astronomy. And then I'm going to focus on their dynamics, how they move, how the stars in them move, a little bit about that, because that's connected to the research that my students and I do at San Francisco State. And then I'll switch gears, as I said, and ask, how can the astronomical perspective that we all gain from the observations we do as amateurs, professionals, enthusiasts, and the work we do as astronomy educators, be used to help us confront the crisis that we have on Earth now. Okay, so first of all, what is a globular cluster? Well, it's a big ball of stars, and this is one of my favorite pictures. It kind of puts them in perspective. In the upper left corner here, what you're seeing is a small galaxy, the Small Magellanic Cloud, which if you've been in the Southern Hemisphere, you may have seen. It's one of the irregular galaxies that's a satellite of the Milky Way quite nearby. And so that's in the upper left. And so you just see the beginning of it in the upper left corner, but then the ball of stars there is called 47 Tucani, and that is a globular cluster. They typically contain some few 100,000 up to a couple of million stars. And there are about 150 of these in our own galaxy. And they are present in basically every galaxy you look at. Some galaxies have many, many more than we do, but we are blessed with about 150 of them. So, what do they do for us? Well, one of the things that globular clusters did for us about 100 years ago now is they were sort of the beacons that were used by Harlow Shapley, making use of work that had been done on variable stars to figure out where we are in the galaxy. And Henrietta Leavitt's work on variable stars enabled Harlow Shapley to figure out how far away the globular clusters that you can see in the sky are. And he noticed that they're concentrated, many more of them are concentrated in the directions of Sagittarius and Scorpius, as many of you may have experienced. And yet there are some of them kind of everywhere, but they're concentrated there. And he was able to get distances to them and figure out their distribution. And he posited that they tell us that they are sort of the sort of beacons of the of our structure. It wasn't known whether it was, the entire universe or just one galaxy at the time, but that they were kind of the beacons of the structure that we're in. And he was able to show that we are not at the center. We are far, far from the center, in fact. And so where are we? Well, we're somewhere here out, maybe, roughly halfway out from the center to the outskirts of our galaxy. We are in the disk, and there's a lot of material, sort of obscuring material that we call dust in the disk, and that makes it hard to see things. And that's really why it took until roughly 100 years ago, a little less, to figure this out, because it's hard to see individual stars very far away from the center, from where we are. But the globular clusters, because they're above and below the plane and they're big and bright, were a lot easier to see. And so that really was a huge leap forward. It took a little while longer to figure out that, oh yeah, we're one galaxy and all those other spiral nebulae are other galaxies. That was controversial for a while, and Shapley was actually on the wrong side of that controversy, which is quite interesting. But anyway, bottom line is, that was one of the first things that they were really useful in teaching us about, where we are in the structure of in our universe, shall I say. Another thing that globular clusters have done for us is that they're really, I think of them as the Rosetta Stones of stellar evolution. They have taught us about how stars live and die, and that's because it really helps to have a whole bunch of stars at the same distance and that were born essentially all at the same time, to kind of remove some of the variables that make it complicated to figure out what the heck is going on. If you're just looking at a random collection of stars at different distances, it's quite a bit harder to figure out. When you do that, when you look at a single cluster and you measure some of the most basic things you can measure about stars, their brightness and their color, which correlates with their temperature, you discover that they don't occupy just any old place on a diagram like that. They produce these very distinctive structures. I don't know if you can see can you guys see my cursor, Sukata or Glenn? Sukata or Glenn, can you see the cursor when I move it? Wondering if I have a pointer or not.
Yes, I can see it.
You see the
we
cursor?
Can see
yeah.
It. Yeah.
Okay, great. Okay, so when you make a diagram like this, you discover that many, many stars are in this part of the diagram that we call the main sequence. That's where stars are when they're fusing hydrogen into helium in their cores. These brighter stars up here are the giants. Those are the ones that with even a small telescope you can see, or medium-sized telescope, you can see the individual stars. Those are the giants you're seeing, the ones that are the very brightest stars in the cluster. And then over here, these relatively bright blue stars are the ones that have begun to convert the next element and get their energy from the next element, helium, by converting helium into carbon and oxygen. And so these are helium burning stars. And learning, all the details of how this works was really aided by being able to make diagrams like this, so-called Hertzsprung-Russell diagrams. That has been sort of the story of the last 50, 60, 70 years in astronomy, major push to study stellar evolution. A lot is now understood about it. There are still unanswered questions for sure, though. Okay, so what else is interesting about globular clusters? Just dynamically, it's an interesting situation, right? You've got a ball of stars, call it 1 million stars. Each one is, tiny compared to the size of the cluster. They're still, even though they're much denser, than the stars in the solar neighborhood, stars are still, pretty far apart compared to their sizes. Instead of light years apart, they're kind of light weeks apart in a pretty dense cluster. In general, they don't collide with each other. Every once in a while they do, though. This is one of the rare places in the Milky Way where stars do collide sometimes. Maybe we can talk about that later. But they're all moving under the influence of all the other stars. So this is an interesting dynamical problem. We sometimes call it the million body problem. How does that work? Is that stable? Will this thing last forever? Will it fall apart? What happens? So there's been a lot of work over the years, starting in the 60s and 70s, a lot of theoretical work on them. And I'm just going to take a minute to show one of the relatively early simulations showing what these things look like. This is a Simon Portuguese Zwarts in the Netherlands, who's a theorist who works on simulating clusters like this, made this. Let me see if this will work for us. Let's see if we've got, there we go. So this is not a million bodies at the time, and even now we're not simulating million body clusters, but this is several thousand stars, and it gives you a sense of what the structure is. They're quite concentrated to the center. The outer part is constrained by essentially the tidal forces from the galaxy, but they're quite large in terms of how far out stars can be and still be part of the cluster. For the moment, he's got time is not advancing. We're just looking around the cluster. Now he's let time go, and so gravity is taking over, and you can just watch how the stars are all moving in response to the other stars. It's like a kind of a beehive in there. You can see stars move in and out of the center. There's kind of a core, what we call it, and then a halo of stars around. What the theoretical work found for many years and has continued to find is that if you think about how is this going to evolve, and you can do it in a computer or you can do it theoretically, you find that that core, let me actually get out of there, that core structure, that core halo structure is maintained for a long time, but that the core will gradually get smaller and smaller and smaller. It will gradually collapse. And that's essentially because as stars interact with each other at a distance, just have lots of little distant interactions, gravitational interactions with one another, they share energy around. And on average, the more massive stars wind up with lower velocities, and the less massive stars with higher velocities. This is called energy equipartition. As a result, the higher mass stars kind of sink to the center, and the lower mass stars tend to be out in the halo part of the cluster. And over time, that core, according to theory, will just keep getting denser and denser and denser over time. And so the question becomes, well, then what? Will they eventually, lots of stars merge, and then eventually you get, and then maybe a supernova, and then lots of mergers of massive stars? What's going to happen? Will you get a black hole? And in fact, there's many predictions that there ought to be black holes at the level of a few thousand or tens of thousands of solar masses in the middle of globular clusters. This has been theorized for some time, and there's been some hints that maybe they're there, but nothing definitive, and it's been actually very controversial. Even the hints have been, there's been a lot of controversy even about the hints. So it's an open question. But if sort of intermediate mass black holes exist, globular clusters would be a place where they ought to reside. So it's quite some interest to see if they do. Okay, so now, interesting point though is that binary stars really affect this story, play an important role in this story. And the idea is this. Remember I was saying that the heavy stars kind of sink to the center as they slow down and slow down and slow down. The issue is that if there are binary stars in there, a binary star is a pair of stars that's gravitationally bound to one another. And they are moving quite fast around each other as a result of that being bound together. And it turns out, if you ask yourself what near, not direct collisions, but near misses between a binary and a single star, what happens when a single star passes by a binary? Well, you can do that calculation. You can do it in a computer. You can do it by hand. And you find that in general, the most common kind of interaction is that the passing star gets a kick. It speeds up. And where does that energy come from? It actually comes from the binding energy of the binary. The binary winds up getting to be a tighter binary. It loses some potential energy, and that is transformed into kinetic energy, the passing star. So that's interesting. So essentially, binaries, if they're in there, they act like little egg beaters. Just keep everything stirred up. And if everything's stirred up and moving fast, it's not going to sink down and make a black hole. And so what simulations show is that the binaries will certainly delay and may even prevent at the current epoch, prevent the formation of black holes. Not clear. It's not, we're not sure yet. And hey, theory is theory, and we need observation to see what's real. So, but it's a really interesting story. And so the point is that we need to know we need to know something about binary populations in globular clusters if we're going to have a feeling for whether these black holes, ought to be in there, or why they're not in there if they're not, or if they are in there, what's the deal with the binaries? Okay, so this is what my students and I, for many years, have been studying different aspects of different kinds of binaries, different aspects of this over the years. And there's just a few students presenting their work at the American Astronomical Society meeting and other meetings. And, the joy of being able to study this stuff, of course, a lot of it is working with young people who are, interested in these questions as well. And so it's been a real joy at San Francisco State to do that. And I don't know how many of you know, but San Francisco State has a combined physics and astronomy department. We have a undergraduate program that's about 25 students graduate a year, physics and astronomy, and a master's degree, a physics master's and a physics concentration astronomy master's. About 10 students a year graduate and go on to all kinds of things, PhDs, PhD programs, eventually professorships. I've been around long enough, a couple of my students are professors other places now. And then community college teachers, planetarium folks, science educators of all kinds, some working in industry, all kinds of different stuff that students do after they leave San Francisco State. So that's a real joy for us. Okay, so what kind of stars, what kind of things have they been finding? We've been finding, well, one kind of binary we've been looking at and looking for are called cataclysmic variables. And some of the amateur astronomers in the group may have heard of these or even looked at some of them. They're kind of interesting because strange and wild things can happen in cataclysmic variables, which is how they got that name cataclysmic. But what are they? They're basically two stars. One normal sort of sun-like star, although typically a lower mass than that, and a white dwarf. And at the center of this disk here, you're seeing is the white dwarf. Actually, you see it better in that little animation, white dwarf there. And these, by the way, these are the two most common kinds of objects in globular clusters. Globular clusters have lots and lots of low mass stars. They're very, very old. I neglected to say that. They do last a long time, or at least some of them do, and survive to this day. They have ages on the order of 12 plus or minus 1, let's say, giga years, so billion years. So lots of stars have burned out. And we find neutron stars in there from stars that burned out a long time ago. And there are lots and lots of white dwarfs in there because most stars leave behind white dwarfs when they die. So the two most common kinds of stars are hydrogen burning normal stars, sun-like stars, and white dwarfs. If two of them are in a binary close together, then the white dwarf can actually steal material from the surface of the main sequence star. And when that happens, you get a disk of material around because there's a lot of angular momentum. It doesn't just fall right down onto the white dwarf. It cycles around for a while. And all kinds of cataclysmic things can happen because it's not a very smooth process. It tends to be very kind of lumpy. And you can get dwarf nova outbursts, in extreme cases, a nova outburst. But in general, what's distinctive about them is that that accretion disk, so-called, around the white dwarf gets very hot near the white dwarf surface, and so hot that the gas actually emits X-rays. and of course, and ultraviolet light as well. And so they're pretty distinctive, even though they're not very bright at the visible wavelengths. They are quite distinctive in their colors and also in emitting X-rays. And so how do we go looking for them? Well, one way is to go looking at X-ray wavelengths. And so this is just, I want to show a few examples of the kinds of data that we take and the kinds of analyses we do. This is using the Chandra X-ray Observatory, which is a spectacularly high resolution X-ray telescope, the highest resolution by far that's ever been produced. And so it's been possible to see, individual stars essentially in globular clusters. We still have to go find which star exactly is producing the emission, but an X-ray image looks a bit different from an optical image. This is just, of course, false color because it's all X-rays, but each of these dots represents one X-ray that was detected. This was a long exposure, about 30,000 seconds we're looking at, so you have to look for a long time to get many X-rays. But you can see where there are a whole lot of X-rays came here and here and here and there. So what are these? So what we do after we get an image like this is we say, okay, we see some sources of X-rays here. What are they? Are these something in the cluster? Or some of them could be behind the cluster. They could be active galaxies with, that are also X-ray bright. They could be foreground stars that happen to be bright at X-rays. So we have to be careful. We can't assume that they're part of the cluster. So what we do is we go get optical data, and clusters are so dense, we've got to use Hubble to see in the middle. And so that's what we do. And so here's some Hubble data. This is just an example of, and actually I can flip back and forth maybe, because these are on the same scale. And so this is the middle of a globular cluster called NGC 6397. It's the second nearest globular cluster to us. And at about 7,000 light years. It's got a very, very dense center. And here is that center. We're looking at it with Hubble. And I've just put blue triangles around the stars that we identified as the sources of those X-rays. And there are multiple characteristics that these stars have that made us say, those are the ones that are emitting those X-rays. And yes, they're cataclysmic variables. I'll just mention a couple and show a couple of crazy looking plots. Of course, we don't just look at the image, we make measurements, it's a quantitative science. And so what do we do? And let me just say, before I show that plot, that you may be able to just discern that the colors look ever so slightly different. Certainly for this one, you might notice it looks a little bit blue. This looks sort of a little purpley. And there's some hints just from the image, which is kind of cool that they're maybe distinctive. And here, by the way, is a light week in this cluster. So this is what I mean about stars being light weeks apart instead of light years apart in the center of a dense globular cluster. Okay, so what do we really do? Well, we make plots. Like the plot I showed at the beginning, this so-called Hertzsprung-Russell diagram. And if you just look at the left panel here, the x-axis is effectively just color. We measure the color by taking images through two different filters, a blue filter and a red filter, and then comparing the brightness of the stars, the magnitudes of the stars in those two filters. And then if you remember the diagram I showed earlier, you could see the giant branch in that diagram, the so-called turnoff, and the main sequence. And now with Hubble, we've got a very, very, very narrow, we can make exquisitely, good measurements. This is that so-called horizontal branch. This is the bluer stars that are helium burning stars, manufacturing new carbon and oxygen right now. That's these right here. But notice now, first of all, we go way down the main sequence, down to very low mass stars, and we see a whole new thing that we couldn't see in that other diagram. I didn't mention that other diagram was M55, globular cluster in the Northern Hemisphere, one of the Messier objects. And from the ground-based observations like that was a very nice diagram made from the ground, a 1 meter class telescope from the ground. You don't see white dwarfs. They're too faint, and everything's so crowded you can't see the white dwarfs. But now we see a whole sequence of white dwarfs right here. And by the way, if you know about magnitudes, 10th magnitude versus 25th magnitude, that's 15 magnitudes. That's a factor of 1,000,000 in brightness. So that's a big range that we have access to with Hubble, and that makes this possible. And so so we get all these white dwarfs, and then all these. What are all these red dots? Okay, these are things that that are the things that we've identified as potential cataclysmic variables. I only showed 5 from that previous plot. That's actually from an earlier study. This is a more recent study of the same cluster in more detail. But the bottom line is that these objects don't land on the main sequences. They don't land on the giant branch of the main sequence. I mean, this one a little bit. I can say something else about it, but in general, they have odd color. They're oddballs in these diagrams. That left panel is the standard Hertzsprung-Russell diagram. The one on the right, I'll just say very briefly, is something slightly different, involving a very narrow band filter that picks out specifically an emission or absorption line produced by hydrogen. And by looking for that, we can actually get a much better sense, or really confirm whether we're seeing what we think we are, because cataclysmic variables really stick out in that they have what are called emission lines. If you look at the spectrum of a cataclysmic variable, you'll see parts of right at the hydrogen lines, you get emission in the hydrogen lines. Normal stars have absorption lines. Cataclysmic variables have emission lines due to the accretion disk. And so that's why these things are all sticking over on the left side. Normal stars, the normal stars that are all here, look very different. So that helps us identify these objects. So that's the kind of measurements we're making with Hubble. And here again are these triangles, are the first 5 of these cataclysmic variables that we found. Another thing I wanted to mention is, of course, part of doing science is part of the fun is serendipity. And so I just want to mention quickly a story of serendipity. As we were looking for these cataclysmic variables, we also noticed some other stars. And you'll see here these, I've put big blue squares around them here. And you'll see they really look quite distinctive in the color image here. And it turned out that these are something completely different. And I won't go through all the details, but I'll just say that it turned out that what these are pairs of white dwarfs, but they're, one of the white dwarfs is an unusual white dwarf and I should say that a normal white dwarf in a globular cluster and in the galaxy in general, most white dwarfs are made of carbon and oxygen. They're made from low mass stars that after they convert, the stars convert helium into carbon and oxygen, they kind of get stuck. They don't go any further. Only much more massive stars will, manufacture all the heavier elements. But most stars get stuck after carbon and oxygen. And so what they leave behind is a big ball, or actually a small ball, Earth-sized ball of carbon and oxygen, very dense. But it can happen that some white dwarfs are made even from stars that never even get to converting helium into carbon and oxygen, that get stuck at an earlier phase, and you're left just with a white dwarf made of helium. And so that's actually, turns out, what these things are. And this is another one of these crazy diagrams. Here's the main sequence, just off we didn't show the whole thing here. These are the normal white, these purplish, dark blue purplish stars are the normal white dwarfs. And what we found are these things are white dwarfs made of helium instead of being made of carbon and oxygen. And they're low mass white, lower than normal mass white dwarfs, essentially because the evolution got interrupted. And I won't take the time to go into the details of this unless somebody wants, but it's kind of crazy and fun. We found this thing we didn't expect. Why is it interesting to us? Because it turns out you really don't make helium white dwarfs in a globular cluster, or really anywhere at present, unless there's a binary companion that causes the stars, its companion star, to have its evolution interrupted. And so this is also a window into the binary star population. So what we think these are white dwarfs made of helium with companions that, for reasons I won't go into, we also think are white dwarfs, just much darker, not visible white dwarfs. Okay, so that was a bit of serendipity that we've been pursuing for some time now, and it turns out these are seem to be quite common, and they're pretty hard to find, but quite common in the clusters where we've been able to look. Okay, so those are binary white dwarfs, one helium and one carbon oxygen white dwarf. I'll just say very briefly before I turn to talk about astronomers for planet Earth briefly. I mentioned that, part of the reason we're interested in binaries is this question of whether there's black holes in the middle of globular clusters. Well, one of the globular clusters where it's been suggested that there is one of several thousand solar masses is Omega Centauri. And so one of the clusters, so we decided to go just look directly for that black hole a few years ago, and a couple years ago. And if there's gas falling into it, that's a big if, then that gas, before it goes over the event horizon of the black hole, ought to get really hot and emit X-rays. And so we took a really long exposure of Omega Centauri for a lot of different reasons, but partly to look for a possible black hole. And so here's an 80-hour exposure. This is, again, an X-ray image. There's a sort of X-ray background, but then all the bright individual things you see there are sources of X-rays. 3 of them we pretty rapidly identified were cataclysmic variables. Okay, but what about, where's the center of this cluster? It's a little hard to figure out. Let me zoom in a little bit. Using other people's results, we were able to identify where the center of the cluster is. There it is. Is there any source of X-ray there? No sign of X-ray, no sign of an excess of X-rays there. And so it was our conclusion from the X-ray side, no sign yet of a black hole in the middle of the largest globular cluster in our galaxy. Doesn't mean it's not there, but it does put a limit. It put a new limit on what might be there. Either it's not there, or it's very low mass, or it's accreting at a shockingly low rate. Okay, so I'm going to leave the sort of science piece of my talk there, and just say that I've had the great good fortune to kind of start my career during grad school. Hubble was launched. As I was arriving at Berkeley for my postdoc, it was repaired, and I had the great good fortune to work with Ivan King at UC Berkeley, who was someone who had been involved in planning Hubble and is kind of had done work on globular clusters kind of his whole career. And so we had a tremendous amount of fun those first few years with Hubble, learning a lot about globular clusters. And so that's been incredible good fortune and pleasure for me to have access to this amazing instrument during this time, and be able to work with lots of people and yeah, just benefit from it. And it's the 30th anniversary of Hubble was last year, so a lot of us were thinking about all that it's done for us. So that said, lately, over the past, I don't know, few years, I and some of those around me have felt like, with this great good fortune we have, we're looking at these things, spending our time thinking about things that are, impossibly far away, right? The nearest thing I think about is, like I said, about 7,000 light years away. Well, a light year, what is that? How many trillion miles is that? 6 trillion, trillions of miles away. So, meanwhile, and you don't want to be that person who's, just looking at the stars. Well, the house is on fire. And it's really kind of been a growing concern for so many of us. What can we be doing? What should we be doing? And of course, we can all do things as individuals. We're working. There are all kinds of amazing groups working on climate. But the specific thing that came to me and some of us recently was, wait a minute, astronomers actually have a role to play as astronomers and astronomy educators and I'm talking astronomers broadly here, all of us who have knowledge of astronomy and who've gained that perspective on Earth that we have from knowing astronomy, can use that, can share that, can bring that perspective to the conversations that we have and the things that we do. Is there anybody else who knows just how far away other planets are? When I see things in the newspaper like, oh, so-and-so is going to find us a new Earth, or, it makes a great headline, but I think, oh my goodness, how many people are thinking that maybe there is some other option? No, we need this planet. It's fantastic to be finding planets elsewhere. It's one of the most exciting areas of astronomy, absolutely, but it is not a solution to the crisis that we face. And so, many of us, and I'm guessing some of you were probably at the Science March back in 2017. Science is such an important part of this story, and unfortunately is not always, and unfortunately we've seen this so much in the past year, not always seen as playing the role that it can and should play. And so in this case, we were thinking at that time a lot about the climate and other things like that. And so that was around the time when we were thinking, wait a minute, astronomers have a role here. And so this is the poster that I made at that time, thinking, okay, astronomers for planet Earth. And so, and just like I said, and just a reminder of just how far away, this is the nearest star, 25 trillion miles away is the nearest star, Alpha Centauri, roughly. And yeah, there are some planets there, probably none of them very nice to live on, but that's the nearest. So we're not going there anytime soon, and we need to take care of this one. Okay, so I'm just checking the time here. So let me describe to you a little bit about this organization that we founded. About a year and a half ago now, the Astronomical Society of the Pacific, which I'm sure many, if not all of you, know of and then have benefited from, such a wonderful organization. The CEO, Linda Shore, a graduate, I'm proud to say, of San Francisco State, came to us a couple years ago and said, hey, we're thinking maybe what would you guys think about having the ASP meeting on the San Francisco State campus? And we're like, oh my gosh, that would be fantastic. So as we were planning this meeting, Linda also said, hey, let's, you guys can organize a session if you want. And so we thought, okay, what kind of session do we want to organize? We want to organize one about this. And so we said, okay, here's our session, Astronomers for Planet Earth, Action for a Habitable World was a session we put together. We brought together astronomers and folks in all sorts of, who were playing all sorts of different roles in the community, on our campus in the community, and folks from the Climate Reality Project together to talk about this in that session. And so that was sort of the start of the organization. We launched the website at the same time. Astronomers for Planet.Earth. It's a .Earth website. I don't know if you've seen those. I actually didn't know they existed until one of the other founders of the organization said, hey, we can use the .Earth. So that was fun. So Astronomers for Planet.Earth. And so what are we doing? And why? And I just want to say just a little bit more about why astronomers. So we have a unique perspective. Astronomers, astronomy educators, folks who, amateur astronomers, citizen scientists, those of us who have that knowledge have a particular perspective we can bring. We have scientific expertise as well. And we're not climate scientists, but we're sort of adjacent to that, right? Some of us actually are climate scientists. There are astronomers, of course, who study climate on other planets. I am not one of them, but some do. But even those of us who aren't, we know what science is. We know how science operates. We know how to interpret, data. We know how to interpret graphs. We can talk about this. We can educate ourselves. I'm not saying, and we're not saying that astronomers all are educated fully about this, but we can educate ourselves and then have a voice. The other thing is, and a big part of this is the realization that, wow, astronomers touch so many people. We teach, God, what's the number? It's, I think it's like 500,000 students or something in the US take astronomy every year. Some really large number, I'm forgetting the exact number. A piece of what we ought to be talking about, right? What does astronomy teach us? It teaches us kind of where we are and where we fit. And it also teaches us how isolated the Earth is. This is the pale blue dot image you may recognize. And just how isolated the Earth is, just how precious the Earth is, how unique the Earth is, how there is no planet B. And so that's a role that we can play. So what are our goals? Well, share this perspective, share that astronomical perspective, help explain the science behind climate change, integrate that into astronomy classes as a sort of regular part of what we should be talking about, share information and solutions to the climate crisis, focus on solutions, learn ourselves about them and share, and then provide astronomers, provide one another, fellow educators with information, because we're not all, in a position to do it like right now. We need help. We need to help each other figure out how to do this. So establish it. We have established a community, sharing ideas, help each other amplify our voices, working together, finding ways to take meaningful action. And then gathering resources to educate ourselves, one another, and then share. Okay, so how are we doing? We've been around for about a year and a half now. We have about 750 members now, and I'm thrilled to say from 42 countries, 17 time zones I learned recently around the world, on every continent. Astronomers really care about this, and there are a lot of people who feel, yes, we need to do something. And what was very exciting for us is, after founding this one locally, very soon thereafter we were contacted by a group in Europe who had similar ideas, and called themselves Astronomers for Future, and then decided to merge with us, and we're just under the Astronomers for Planet Earth umbrella. Similarly, a group some folks in Australia had been working on these issues. There are folks all over who've been working on these issues already. So really, we're just coming together to help each other figure out how to do it better. And so that's the organization. And like I said, this is students, educators, researchers, amateurs, writers, citizen scientists, folks working in all sorts of different settings. Museums, planetariums, universities, colleges, high schools, folks, the members that we have are from in many, many different settings. Okay, so this is a little bit about current projects. We've have a video series you can find on the website. I probably won't have time to show one today, but you can take a look at those. Those are ones if this is something that matters to you, these are ones you could share. They're typically 3 to 5 minute videos that say something about, bring this issue forward using the astronomical perspective. How are we communicating? How are we working with each other? We've created a Slack space and we have a listserv through something called groups.io. And then we've got a set of working groups, people working in different areas, education working group, a multimedia PR working group, etc. Just put out our first newsletter. The other thing that we've been doing is going to conferences and presenting things about it, and organizing special sessions. So the European side of the organization organized at the European Astronomical Society a one-day session all about things related to this, and also preservation of dark skies. We presented at the ASP meeting back in December 2020. And we've got a webinar series going. that is designed to, again, help us educate ourselves. So we're bringing in people who have knowledge, more knowledge than your average astronomer or astronomy educator, so we can become better informed and better communicators about climate. It's different to talk about climate than to talk about astronomy. As my collaborator here, Travis Rector at University of Alaska said, you can go and talk to people about black holes and they'll just, they'll believe you, but you start talking about climate and it's, then it's a different story. People don't, have quite the same reaction necessarily. So it's different to learn how to communicate effectively about these issues. So we're working on that. We're all working on that. And then, as I said, videos that we're making, and various things on social media. Okay, maybe I'll leave that there, and just say, I'll sort of end with this slide. Like I said, this is the organization. If it interests you, join us. If you're curious about it, go check out our website. If you're just interested in what we're up to, follow us on whatever your favorite social media is. We're at Astro for Earth. And yeah, I'd love to hear your thoughts. And like I said, I set up a Google Doc so that if you don't get to ask your question or make your comments, now feel free to share your thoughts on the Google Doc. If you're interested in joining us, and we have weekly meetings of the North America group on Fridays, if you're interested in those, you can put your name down on the Google Doc or email me. My email is on the Google Doc. Yeah, and I'd love to hear your thoughts, and I'd like to open it up to questions. Sukada, I'm not hearing you. I don't know if that's don't hear you. There we go. Yeah.
She just posted the link to the Google Doc.
It's funny, you don't look muted, but I'm not hearing you.
Can you hear me? You should
I
be able
hear
to
you,
hear me.
Glenn. Yeah.
Okay.
Yeah.
Well, in reverse order, while we're waiting for her to jump in here.
You bet.
Are you there?
Yeah, can you hear me?
Now
Yes.
I can.
Okay, all right,
Go.
great. I don't know, my AirPods acted out, I think.
Okay.
So I was just saying that it's a wonderful project. Like, I'm really thrilled to hear about this because I think it can have a huge impact just from a perspective of, oh, these are astronomers who study the space and the exoplanets and all other places. And they are telling us that you better take care of the Earth, the one planet that we have. There is nowhere else to go. So I think that can have a huge appeal and huge and something that you mentioned really struck the nerve with me, where when you talk to people about black holes, they believe you. But when you talk to them about climate change, they don't believe you sometimes.
Yeah.
Or they don't take it as seriously.
Yeah.
So that's definitely something which is interesting, intriguing.
Yeah. Yeah.
So I did share your Google Doc link in the chat channel.
Yep. Great, thank you.
And
I won't be able to look at it right now. So, but anyone, please feel free to put any thoughts in there. But of course, I'd love to just answer questions if you put them in the, I guess on the YouTube thing, there's a way to put questions.
Yes. I hope people add their notes and information in there for your mailing list and for more information on this project. And as for questions, we do have quite a few questions in the chat channel. So I guess I'll start from the first one. It says, what is the solar mass cutoff for helium white dwarfs to carbon oxygen dwarfs?
It's about a half a solar mass, a little less than that. So essentially, when a star is climbing the giant branch, it's putting more and more mass into its core, adding more and more helium to the core. And as it goes up more and more, because at that time it's fusing hydrogen into helium in a shell in a around the edges of the sort of proto white dwarf at the core. And so as it's climbing up, when it reaches the tip of the giant branch, that's when the core is about a half a solar mass, maybe a little bit less. And that's when helium ignition occurs, and you start, and the core starts converting helium into carbon and oxygen. So if it reaches ignition, if it goes all the way up to the tip of the giant branch, reaches ignition, then it'll wind up turning into carbon and oxygen. But if it's less than that, if it gets interrupted from climbing that giant branch, if that gets interrupted by the presence of a companion star, which is what happens in these scenarios, then the helium ignition never occurs, and instead you're left with the core of the former giant in a binary. Actually, what happens is the giant's envelope engulfs the companion star. The companion star feels drag, starts cycling in, heats up the envelope, which is expelled, and then you're left with the former core of the giant, made of helium, which becomes the helium white dwarf, and the companion star in a binary, type binary.
I see.
Thank you for that question.
Okay.
Yeah.
The second question is, I think, written in two parts, so I think I'll read it in its entirety. With stars in clusters being relatively close proximity from each other, like light weeks, hypothetically, if our solar system were located in a cluster, would the night sky we see on Earth appear more spectacular, filled with neighboring stars at brighter magnitudes?
That's a lovely question. Yes, I had asked that question myself as well. And the answer is that there would be, I mean, it depends on the cluster, of course, but in one that I did the calculation for once, it would be like many Venuses, many really bright, Venus-like objects in the night sky. It wouldn't necessarily be too bright to see other things, but Venus is pretty spectacular when it's bright. And yeah, there would be lots of really bright things like that.
Oh, cool.
Yeah.
Next question is from Jim. What are theories of formation of star clusters?
Oh gosh, that's a good question. And there's a ton of activity in that area now because of something really interesting that happened. So I'll give a slightly long-winded answer if you don't mind to this. So when I went to grad school, I was taught that globular clusters, when they're born, all the stars are born at basically the same time, and they all have identical chemical composition as a result. And the result of that is you get these very, very narrow main sequence, narrow giant branch, and all that. Now, the amazing thing that happened is when Hubble went up and it was possible to make really, really accurate measurements. This was actually first done by a guy who was a grad student at Berkeley when I was a postdoc. You can make very, very accurate measurements of the colors of stars. You actually discover they're not quite chemically identical. There are slight changes, differences. And those differences turn out to be really hard to explain. So the broad picture is reasonably well understood, right? It's as the galaxy is forming, as this big cloud of gas that forms the Milky Way forms, the globular clusters form while that collapse is occurring. And so since the stars form early, even before the disk forms, they wind up with these very big orbits in all different orientations. They're not going in circles sort of like the disk is, all in the same plane. They're in all different orientations. And that's because they form even before the disk forms as the cloud of gas that forms the Milky Way is collapsing. The details, however, are so that big picture is pretty well understood, but the details are kind of really pushing theorists to the limit right now to try to understand the kinds of chemical variations that are now being discovered using very accurate measurements with Hubble. Yeah. So it's opened up a whole new can of worms that's keeping theorists busy.
That's a good thing.
Yes. It's always exciting.
Yep. Next question is about Sirius. Were Sirius and Sirius B always around 8.30 AU apart, astronomical units? So, or were they further apart in the past? Is there a disk around Sirius B with the material from Sirius?
Oh gosh, what a good question. Yeah, so are you saying that you know their current, because I don't know offhand their current distance. Are you saying?
I will have to look
I
it up.
can't.
And specify.
Yeah, I mean, there are several I know there's several arc seconds apart, and Sirius is quite nearby. I forget the exact distance. So I'm going to just, so it's probably, yeah, it's going to be in the AU's, range, current separation. And so that is a great question, and I don't know the answer. So, because I think fundamentally your question is, wait a minute, are they close enough together that when the white dwarf that is Sirius B formed, it would have had to be a giant that was big enough that it would have engulfed Sirius A? And I should know the answer to that question, and I don't, so I'm going to have to check. I thank you for that question.
Well,
if it's within, I mean, I'm guessing that the answer may be yes, because giants get to be of order 100 AU, and that's going to be bigger than the separation, and so it may have been through a so-called common envelope phase. Yeah.
The distance, actually, the separation is 31.3 AU.
Yeah. So that's
as
close
reported
enough.
in Sky Safari.
Great question. Thank you. It may have been through common envelope. The only thing I'm not quite sure is a little surprising about that is that in typical sort of common envelope scenarios, the companion comes in closer than that before the envelope is ejected. So now I'm going to have to look into this.
Cool.
Yeah.
Interesting question.
Yeah.
Well, I can't tell who asked that question, but feel free to follow up with Dr. Cole on this.
Yes.
If you have our email address. Next question is from Shilpi. How are star clusters different from satellite galaxies?
Yeah, it's interesting. Broadly speaking, in general, galaxies are bigger. But, so for example, that slide I showed at the beginning, you could just see this sort of edge of a small satellite galaxy called the Small Magellanic Cloud. It's a lot bigger than globular cluster. One difference, I think the biggest difference you can say between globular clusters and galaxies, even the small galaxies, because it turns out galaxies can be very small too, is dark matter. So galaxies in general have dark matter in them. Globular clusters, all the dynamics can be explained without dark matter. So they do not seem to have dark matter in them. So that is certainly an important distinction. Yeah.
Then people are definitely clicking your Google Doc link. So
that's great. Please put in any thoughts you have. I'd welcome. Yeah, and of course you can always just join the organization if you want to by going to the website and clicking join and filling out that. But you can also just add your name on this Google Doc if you like.
Good. Then I think I have a couple of more questions here. Next question is from Tex. Within a cluster, is there a tendency for stars to capture each other and form binaries? And then it seemed like the binaries force other stars out of the cluster. Is there a net capture versus expels?
Oh, this is neat. Okay, so that is sort of two-part question. So the first part, so I love that question. The first part. There's, in fact, when I was studying this early on, it was partly because my thesis advisor, my PhD advisor, had been kind of promoting an idea or thinking about an idea of tidal capture, so-called. So if you want two things to come by each other and capture each other, it's not that easy, right? Because when they come close, they're moving really fast. They've been pulling on each other, right? And so they're accelerating, and then they go whizzing by. If it's just two billiard balls that can't respond to each other, can't raise tides on each other, then they'll just whiz by, unless they actually collide physically. They'll whiz by and just, they're not going to capture each other. But there's a phenomenon called tidal capture where they could start whizzing by each other, and then if one or both of the stars has tides raised on it, that can dissipate some energy such that the other star won't just go whizzing by and never come back. It could, enough energy could be lost in the tides or converted to, the tidal energy, that the passing star would then stop before it, goes off to infinity, and then come back, and then more tides could be raised, and they could capture one another effectively if tides can be raised. So there's a lot of work on this in the sort of 90s and 2000s, and what it looked like is, from simulations that people did, is that there's a pretty narrow window. Like if you get too close, those tides get raised, but then the star gets engulfed. You just wind up with a merger. If you're too far away, you don't raise tides that are big enough to dissipate enough energy to get a capture. So there's a pretty narrow window, like between maybe 2 and 3 stellar radii, something like that could do it. It's still not answered completely if this happens. But it's still a possibility that's out there. What the more common scenario, it now seems, to create cataclysmic variables in particular, and all kinds of interesting binaries, is something we call exchange interactions. So if you start with a sort of standard binary made of 2 main sequence stars, you have a interaction with a passing star, that passing star can knock one of the main sequence stars out and become the companion of the other star. So basically exchange partners. That is a very common scenario in numerical simulations. You see this all the time, and I know I'm getting on. This is not quite your question, but I'm going to mention it anyway.
That's totally fine.
Because many of you, I'm sure, will have heard of the discovery by LIGO of binary black hole mergers, which is just, this mind-boggling new area of astronomy and physics, being able to study gravitational waves. And I, don't have time, and I didn't wind up including in my talk. I do have some, pictures here, but I won't take the time to show them unless somebody wants me to.
Maybe we will have you back for another talk.
So anyway, but I'll just say that one way you can get those binary black holes is to go through a series of exchange collisions and wind up with pairs of black holes. And so anyway, bottom line is tidal capture is thought to be possible. It may be very rare. There are other ways to get interesting interactions to happen. Your other part of your question about stars getting kicked out, it is the case if through those exchange interactions, sometimes that third star can get a big kick and just escape from the cluster. One thing I didn't mention is that just over time, stars do get kicked up to high enough velocities that they have escape velocity, and then they just leave the cluster, or they wind up in a big tidal tail kind of the cluster. So that does happen. We see signs of that, and we think actually that there used to be quite a few more globular clusters, and that some of them have just fallen apart over time through this evaporation, we call it. Yeah.
Great. And I think I have one more question for you from Ronald. Like galaxies, can star clusters merge if they're close enough?
Absolutely, they could. Yeah, and it's been toyed with as a possible explanation for some of the, it's one of the ways people have tried to explain some of these weird chemical things that have been seen. But it's so common to see these chemical signatures, like distinctive chemical signatures, that it seems like mergers can't explain that, at least not most of it. But absolutely, 2 globular clusters, if they come together, could merge.
Cool.
Yeah.
Great. Yeah, I think that's all the questions I have. Okay. But we really appreciated you joining us today and giving this wonderful talk. And hopefully next time we can have you back to talk about gravitational waves and more about this project. And sure. I promise I will set up a Zoom session with everyone in there.
It's fine. It's fine. It's all good. I'm sorry not to see the faces, but hopefully it was enjoyable and interesting for.
Oh, definitely. Yeah, I assure you, I think everyone appreciated the talk a lot, and I'm getting a lot of comments on the YouTube channel just thanking you for giving this wonderful talk.
Well, thank you for inviting me.
Yes, no problem at all. Our pleasure. So I think with that, thank you everyone for joining, and I'm glad that you all could spend your Saturday evening with us, and please do keep an eye on our keep an eye on our meetup page and to find out more about our future events, and we will definitely keep you posted. So thanks again. Good night.
Good night. Thank you, Sukata. Nice to meet you.
Yep.
Thank you, Glenn.
Thanks, Glenn.